Linear function pattern recognition. Today we're going to continue to talk about rate of change from a table, as well as finding missing values or extending a table of values using rates of change. The focus today is when we have jumps in our table, and specifically not uniform jumps. For each of these tables below, we are going to fill in the blanks and identify the rate of change, the unit rate, and identify the type of function represented. We're not necessarily going to do that in this order. Every time you see a table, where do you start? We always start by doing the change in x and the change in y to see what type of function we're dealing with. And you only have to do the change in x and the change in y for the values that you have. So for example, we are going to be finding all of these change in x here because we're given all of those x values. But for the change in y value, we're going to look between 120 and 108, and then we're going to look from 108 to 40 and from 40 to 4. Please do that now. Hopefully your values match mine with your change in x's here and your change in y's here. Remember, you can use your number line to see, is it increasing or decreasing? -5 to 3 is going to the right, so it is increasing. -2 to 1, increasing by 3 again, and so on. You can imagine that 120 would be over here and that 108 would be further to the left, so that's why it's decreasing, or you can see that those numbers are getting smaller. So we still can't at a glance, at least I can't at a glance, notice whether or not this is a linear function or whether or not it has a constant rate of change. So I need to look at these pairs. So I need to see, what do I have in my table? So I can find the rate of change between this change in y over change in x. So remember, rate of change is always the change in y over the change in x, and we need to see if it's constant in order to know if it's linear or not. So we're looking here, and we have to see, okay, our change in our change in y is -12, our change in x is +3, and we're going to compare those. So it's a good idea to reduce those fractions. So for example, my 12 over 3 reduces to -4 over 1. And what I need to do next is looking at the change here. But the 68, the next thing I have is actually all of these values here. We have to look at what are these x values here all add up to be. So you're going to add the 20, the 3, the 4, the 3, the 2, and the 5 to see what that comes out to. And when you add all those up, hopefully you will see that you have, paired with our change in y, which is -68, that all of those different x values add up to +17. And if you divide -68 by 17, it comes out to -4, which we can put that over 1 because that means 17 went in there evenly. And then our last group here, our last pairing, is -36 over +9, and you might recognize that already, but if you divide that out, you're going to get -4 over 1 again. If you divide it on your calculator, -36 by 9, you're going to get -4, but that is the same thing as -4 over 1. So I put that on my sticky note. Now I want to summarize that right here where you would write it for your notes. We're going to summarize all that right here. Now we need to look at what are these missing values right here, and it matters what these changes are. So let's take a look at that. So I zoomed in a little bit and erased some work just to make it more clear for you. Your paper might not have been as messy as mine got. So when I'm looking here, I can see that for this difference right here, I am looking at an increase of 3 for my x. And so if you think back down here to our unit rate, and let me resize that a little bit so you can see our unit rate on there, you can see that it's negative 4 over 1. That means it's a decrease of 4 in the y for every increase of 1 for the x. And so when I'm going from here to here, I went 3 for the x, so I have to go 3 for that change in y. And my change of y is changing negative 4 for each one for x, and I have 3 different x's, so I'm really going to be decreasing by 12 here. So 108 minus 12 gives me 96. When I'm looking at the next one, and maybe I'll just change color there, I'm looking at a change in x of 4. And so for each x, I have to change, I'm decreasing by 4 for the y. And so I have 4 of those changes, so I need to multiply that by 4, and I'm going to decrease by 16. 96 minus 16 gives me 80, and I would keep going in that way. So I'm looking at this, we've already done a change in 3, so every time x changes by 3, y is going to decrease by 12, so I know that that's going to decrease by 12 right there. And so 80 minus 12 is 68. And then I'm decreasing by 2 for that last one. And so if I'm decreasing between here, for each x, I decrease the y by 4. I have 2 of those, which means I need to decrease by negative 8 or decrease by 8. And 68 minus 8 is 60. And so that is where our table goes. We could double check here to make sure that that makes sense. We could see, well, is this change what it was supposed to be? And you might have that in your, oh, we didn't do that one before. So by 5, if I'm going from negative 4 for each x, and I have 5 of those x's, that would be decreasing by 20, and 60 minus 20 is 40. So this does check out. Now we're going to take a look at number 5. And again, we are always going to start with our change in x and our change in y. Please do that now. So our first order of business is looking at the rate of change, and we're looking at whether or not these values, change in y over the change in x, are constant, to know whether we have a linear function. So the only 3 that we can check out are right here. So please find the rates of change for those 3 pairs. So zooming in on question 5, you can see the rates of change here. So negative 25 over 5 I've written here, negative 15 over 3 I've written here, and negative 10 over 2 I've written here. And our job now to know if it's a linear function or not is to see if they can be written as equivalent fractions. Can we reduce those ratios or that fraction to see that those are equivalent? Since 5 goes into 25 5 times, this can be reduced to negative 5 over 1. Since 3 divides evenly into negative 15, this also reduces to negative 5 over 1. And since 2 divides evenly into negative 10, negative 5 times, it's also negative 5 over 10. So I can see here that my unit rate is negative 5 over 1, and that each of those fractions were in fact equivalent. That tells me that this is a linear function. Now it's time to fill in my missing blanks. So now to fill in these blanks, I'm going to look at continuing my pattern here because I think that'll be the easiest to go. So I'm going from 10, negative 27, this point right above. I'm finding a typo here or something I miswrote. From 10 to 15 is not changing by 15. It is just increasing by 5. So I'm just going to write over that right there. So my unit rate tells me that when my y value decreases by 5 for every 1 increase in my x. So my x is increasing by 5 here, so I need to do 5 times. So let me get my pen back. So it's going to be 5 times that change of negative 5 that is supposed to be for each one of my x's. And so that means I'm going to decrease by 25. Now, in your number line, If you are decreasing from a negative number, you're going further to the left. So we're subtracting 25. Negative 27 minus 25 gives us negative 52. And now we have to work in the other direction up here. So I'm just going to come right up here, and I can see that from here to here, I'm looking at that positive 3 is my change in x. And for each change in x, I'm going to decrease by 5 for my y. So I'm going to take that 3 times the negative 5, that's negative 15. That tells me that I need to decrease from the one above. That also means I can increase going this way. So I'm going to take my 23 and I'm going to actually add 15 to that, and that's going to give me 38. And then I can check that by going 38 minus 15 does give me 23. So we have some backwards working to do on these problems. Take a minute and see if you can figure out these other two. So here our change in x is 4, and for each one change for x, my y has to change negative 5. So that's why I have 4 times negative 5, which is negative 20. And because I'm working backwards, because I have the number below that, the 38, I'm going to take 38 plus 20, which gives me 58. And to double check that, 58 minus 20 gives me 38. So that is still working out in our pattern. And then the last part that I'm going to look at is where I'm just going 1. So I actually just have that my change right here is going to be just negative 5. And so I have 58 plus 5 because I'm working backwards, and that's going to give me 63. You can double check that. 63 minus 5 does give me 58. So that is correct. For the last question, I want you to do the change in x and the change in y for each of these parts of our table. Now you need to check your rate of change to see if this is a linear function, to see if your rate of change is constant for these inconsistent jumps. So you can see my change in y over change in x is negative 3 over 9, negative 11 over 33, and negative 9 over 27. Each of these reduce to the same fraction. The numerator divided evenly into the denominator, the top divided evenly into the bottom. They all went in 3 times. So it reduced to the same fraction of negative 1 over 3. Now this is not our unit rate. For a unit rate, we have to be something over 1. So it has to be divided over 1. So all you ever have to do for that is to divide negative 1 divided by 3. Divide whatever your change in your change in y over your change in x is, and put that in the numerator. So this is going to be a decimal. I'm going to write this as 0.33, even though that decimal goes on, and it would be negative. It would stay negative. You could write it as a fraction within a fraction. That would be negative 1/3 over 1. But I think we're used to seeing it as a decimal, as in, a unit price at a grocery store or something like that. So it would be a decimal over 1 in this case. And because they all simplify to the same thing, we know that this is a linear function. One quick thing that I forgot to note as we went through this. So because these all reduce to the same unit rate, we know that our rate of change is constant. And I would just like you to note that. So for each one of these, our rate of change was constant. I would write that either above that or in your margin to show rate of change, because that's the description that we want with our rate of change. That's what lets us know that we have a linear function. 2 quick things on our summary. First of all, the jumps do not need to be the same. So my jumps here, 3, 3, 4, 3, 2, 9. They don't need to be the same in order for a function to be linear. These were all linear and they all had inconsistent jumps, but the rate of change was consistent throughout the table. When you reduce them, they all reduced to the same unit rate. That's what makes something linear. And lastly, you can have a decimal or fraction within your fraction for the unit rate. Unit rate means it has to be something over 1. So this reduced to a really nice fraction of negative 1 over 3, which is fine to think of it that way, but the actual unit rate is something over 1. That's why it is negative 0.33 over 1, or you could have that negative 1/3 over 1 just to make it a unit rate.